Hello and welcome. In this video, we're going to take a look at a definite integral of a vector function. We've already seen how we can take the derivative component-wise. How is it that we just take an integral of a vector function? Well, we have the fundamental theorem of calculus for vector functions, and it looks a lot like what we're hopefully expecting for just having this be like a normal function. We have r of t being our vector function. We can integrate that from a to b with respect to t. And it is simply just a matter of finding an antiderivative. So we understand how to take the derivative of a vector function. Capital R prime of t would have to just equal r of t. And then we evaluate that from a to b by subtracting capital R of b minus capital R of a. Now, if we just wish to find an antiderivative, then we can still use our classic notation of the indefinite integral. And in that case, we'll omit the interval from a to b. Now, if we're looking at three-dimensional space, where we have a position function, let's say, being f of t, g of t, and h of t for the three components, this would be just equivalent to integrating each of those as a definite integral from a to b. Again, this is using the idea of the definition of a definite integral being using sigma notation and sums, and, well, we have that nice component-wise addition property for vectors as well. So we really just take that limit and we take that sigma notation and we can apply that to each component, and that will give us the definite integral of each component. So let's take a look at an example from a previous video. All right, in a previous video, we talked about the position of a particle. Well, let's take a look at the velocity of this particle. And we can actually calculate this in our derivative of vector functions video. The vector, let's say, for velocity at time t is given by negative 2 pi sine pi t, 2 pi cos pi t, and negative 2t from t 0 to 3. Let's evaluate and interpret this meaning of the definite integral of that velocity function from t equals 2 to 3. So first of all, really just looking at above here, we're only going to be using that definite integral on each of the three components. So we apply that rule, and then in these first two integrals, we'll have to do a little substitution. Make the substitution u equals pi t, and well, that's just going to basically cancel out the pi that we see in front, that negative 2 pi and the positive 2 pi in each of those integrals. Through a substitution, we should just end up with a 2. Now, I haven't shown those little substitutions here, but you can always double check by taking the derivative that in fact these are antiderivatives. And then, of course, I just have a power rule for negative 2t to get negative t squared. Now, it could also be a lot more compact notation to simply just write this as a vector function evaluated from 2 to 3. You can see that this is essentially like capital V of t. It's the antiderivative of our lowercase v of t. And we can double check that the derivative of capital V of t is equal to this velocity function. So this is an antiderivative, and now we just simply evaluate from 2 to 3. Plugging in t equals 3, we get the vector negative 2, 0, negative 9. And plugging in t equals 2, we get the vector 2, 0, negative 4. And then subtracting component-wise, we see that the definite integral of our velocity function from 2 to 3 is simply the vector negative 4, 0, negative 5. All right, now it's time to interpret what that means. Well, thinking about this as velocity is helpful because velocity is simply like the change of position of a particle. So v is the derivative of our position function. So instead of using capital V of t here, well, if v prime of t is equal to velocity, we can think about this as being a position function. We know that the derivative of position is equal to velocity. And then changing from t equals 2 to t equals 3 and plugging that into position, this gets us the net change in position. So hopefully this kind of brings back the net change theorem from single variable calculus to mind. It's the same idea. If we have a rate of change of some vector function, such as like velocity being a rate of change of a position vector function, then by integrating a rate of change of position over some time interval, we get the net change in position. So, that can be applied to more than just velocity. Whatever this vector value function is, if that vector value function can be interpreted as the change of something as a vector, then by integrating it over a time interval, you end up with the net change of that vector function. Well, it gives you the general idea. That's just integrating component-wise, essentially. It's just definite integral one component at a time. And you can do that for as many dimensions as you want. Well, thanks for watching, and I'll see you in the next video.